The second test targeting absolute convergence that I want us to discuss is this so-called root test. Now, as you will see, the idea of it is, again, comparison of a given series to the geometric series, and its range of applicability is exactly that of a ratio test. So if, for example, the ratio test is inconclusive, it doesn't make sense to apply root test because it will be inconclusive as well. So now let me state the root test so that you can see the parallels between it and the ratio test. So first, let's say we are given a series, sum of AKs. And we would like to consider the following three possibilities. First one is that the limit as k goes to infinity, the kth root of the absolute value of AK is equal to a finite number L, which is less than 1. So if this is the case, then the given series is absolutely convergent. Just like the ratio test, this test here only targets absolute convergence. It can only detect absolute convergence. Condition 2, possibility 2, is, let's say that the limit k goes to infinity of the same expression is a number L which is bigger than 1, including the possibility that L equals plus infinity. Then the series is divergent. So you see that these are direct analogs of the three possibilities in the ratio test. So the third one is, unsurprisingly, going to be that when the limit of this expression is exactly 1, the test is inconclusive. That is to say, it doesn't tell you whether the series is convergent, and you have to resort to other convergence tests to determine that. So the principle here is exactly the same as for the ratio test. If you think about a geometric series, then the values of these limits are just the common ratio. So if you evaluate such a limit for a geometric series, you will get R as the output. And so this is the case. Now, for general series, this is not the case because there is no such thing as the common ratio. And therefore, you just have to think about the limit as the analog of the common ratio, but the behavior of series is determined in the same way by the value of this limit. So if the limit is less than 1, it's as if the common ratio were less than 1. And similarly, if the limit is strictly bigger than 1, then it's as if the geometric series that you're comparing to had the common ratio bigger than 1. And so this corresponds to the case of divergence. And finally, if the limit of this expression is exactly 1, then the test is inconclusive, basically because you don't know from which side the sequence is approaching its limit. So it can be approaching the limit from above, it can be approach the limit of 1 from below, and depending on that, more or less depending on that, the series is can be both convergent or divergent, and it's impossible to determine in advance. So if one of these two series, the root test or the ratio test, is inconclusive, then the other one is going to be so as well. So if you tried one of them, it failed, doesn't make sense to try and apply the other one. Let us now look at an example of application for the root test so that you will see when it is appropriate to apply it. And so the root test is specifically suited for expressions like this one. So suppose you have to test for convergence a series that involves raising some expression to the kth power, or to a power that depends on the subscript k. And then specifically for such cases, you have the root test. So you could in principle apply a ratio test, but it would be significantly more troublesome. So on the other hand, for the root test, which we're going to apply now, things are much easier. So notice that we have to compute kth order root of the absolute value of ak. So that is the so first of all, the absolute value of ak is ak itself. So we have to take the kth order root of this expression here. And so of course the kth order root cancels out with the kth power, and we have simply 2k plus 3 over 3k plus 2, which means that when it actually comes to computing the limit k going to infinity of this expression, then all that we have to do is to compute the limit as k goes to infinity, the expression that was just obtained here. And this is a very simple rational function. We can divide through by k, and clearly the value of this limit is 2/3. Now the important part, of course, is that 2/3 is less than 1. And so by the root test, this series is convergent. In fact, it is absolutely convergent, which is an even stronger property. Of course, here we have a series with no negative terms, so absolute convergence is exactly the same as convergence, so it's not particularly important, but in general, whenever the root test gives a positive answer, then it necessarily tells you that the series is absolutely convergent. And so this is how we answer the question about convergence for this series. We have determined that it is convergent, in fact, absolutely. So you have seen now the notion of absolute convergence and two tests targeting specifically this type of convergence, the ratio test and the root test. Depending on the specific form of the kth term of your series, you have to choose between these two. Basically, the idea is that for ratio test, the especially suitable series are those that contain constant base, say some constant number raised to the power k, factorials, whereas for a root test, the especially suitable expressions are those that contain some complicated expression raised to the kth power, or to a power that depends on k. So then it is appropriate to apply the root test. So this concludes our discussion of these two convergence tests.